To see if the causality problem is solved in quantum field theory, we will use the property that when two operators commute, they can be measured simultaneously. This means that the order on which we apply the operator, so if we start with A and then we apply B, or if we start with B and then we apply A, doesn't matter. So measuring A does not impact the measurement of B and vice versa. For simplicity, we will stick to the case of three scalar Hermitian fields. We will probe causality using the following operator. This will tell us if there is a correlation between the action of the field at the origin and the action of the field at a later time at a different position. And in particular, we know that the field operator creates and annihilates particles. So this commutator will tell us, for instance, if a disturbance of the field created at the origin can propagate and be later annihilated by another action of the field. If this is the case, then this commutator will not be zero. But if it is zero, it means that whatever we do at the origin has absolutely no impact at a later time at this position. We will consider two cases. The first one where the interval between these two events is time-like, and the second case where it is space-like. In this case of a time-like interval, we can expect that the disturbance of the field created at the origin can propagate and be annihilated later in X. This means that if we act the field operator first in X, we should not expect to have an impact at the origin because the disturbance of the field should not be able to propagate backward in time. So there is an asymmetry. If I apply the field first in the origin and then in X, I don't get the same thing as if I apply it first in X and then in 0. Therefore, I expect this commutator to be non-zero for a time-like interval. If we now consider a space-like event, however, we do not expect the disturbance of the field we create at the origin to have an impact in X, and that's because that will go faster than the speed of light, and therefore that will break causality, because we could always find an inertial frame where X will happen before the origin. So in this case, we expect the commutator between phi of X and phi of 0 to be equal to 0. Meaning that applying phi of 0 before phi of X does not matter. It should give the same thing as if we apply phi of X before phi of 0. To verify this, we now calculate the commutator explicitly. So we need the expression for the field at the origin and the expression for the field at X. For phi of 0, the exponentials are just 1 because t and x are equal to 0. So we see that the commutator will involve commutators of a of k and a of k dash, which is 0, commutator of a dagger k and a dagger of k dash, which is 0. So the only commutators which are going to survive are those for between a of k and a dagger of k dash, and a dagger of k, a of k dash, which are both going to give a delta function in k minus k dash. One of the integral is going to be killed by the delta function. The commutator between a and a dagger is just the delta function. Therefore, this term gives us plus times the exponential minus I omega kt minus kx. While the commutator between a dagger and a is minus the commutator between a and a dagger, therefore we have a minus sign, and we will have the exponential plus I omega kt minus kx. So let us first look at the time-like interval case. We can always find an inertial frame where we boost x and put it to the along the time axis, and if we do that, that gives us a simple expression for the commutator. We don't need to solve this integral explicitly, we only need to show that it is not a zero in the general case. The dependence on k only appears through omega k, which is even in k. We recognize the sine function in the numerator. In general, this integral is going to oscillate, and again, we don't need to solve it exactly, but if you want to see its solution, you can look at Peskin and Schroeder. So in general, this commutator is not zero, as we expected, and for the time-like interval. Now, let's look at the case of a space-like interval. And again, for simplicity, we will boost the event in x to put it along the space axis. Now the denominator is even in k, but the numerator is a sine function in k, which is odd in k. And therefore, the integral going from minus infinity to plus infinity, we see that it has to give us a commutator which is 0. This is what we expected, and that tells us that whatever we do somewhere to the field will have only an impact inside the light cone, not outside. So we showed that in the case of a free scalar field, non-Hermitian, obeying the Klein-Gordon equation, causality is preserved. In the case of a non-Hermitian field, the situation is a bit more complicated because we cannot take A dagger as a Hermitian conjugate of A anymore. In that case, we will find that a disturbance of the field corresponding to a particle can actually go faster than the speed of light and leak out of the light cone. But so we'll also do disturbance of the field for non-T-particles. And whenever we measure observables, we cannot distinguish between particles and non-T-particles necessarily. We have to measure the field itself, and causality is then preserved by the fact that the disturbance of the field corresponding to particles and non-T-particles cancel outside of the light cone. So it's an interesting consequence that we need to have antiparticles for causality to be preserved in quantum field theory, at least for non-Hermitian fields.